Hello everyone, in section 1.1 we will study basic properties of probability theory. The outlines of this section will be the main four topics. We will learn basic terminologies used in set theory, basic terminologies used in probability theory. Then we learn basic axiom of probability, and finally we learn basic properties of probability theory. Okay, first topic about basic terminologies used in set theory. So in set theory we will talk about set. So what is a set? Set is a collection of unordered objects. The objects in a set are called elements or members of the set. We usually use capital letters A, B, C, or even H when needed to denote sets, and lowercase letters to denote members of sets. We will say a set contains its elements. In terms of writing, we will write X with this symbol, which is read belongs. Okay, so this whole thing is read X belongs to A. That means X is a member of set A. And then we use the notation, similar notation, but now with a forward slash on top, right in the middle of the belongs to symbol. This means that the number X does not belong to set A. In other words, it is not a member of set A. And occasionally we also talk about the largest set of all, which is called the universal set, usually denoted by capital letter U. This is a set containing all objects under consideration. And sometimes, to avoid confusion, it is important to specify U explicitly. There are three common ways to describe a set. The first way is by listing. It's very simple. If a set H has only finitely many members, and not just finitely in general, it doesn't have a lot, just maybe below 10, then we can list all of them between two curly brackets. Obviously, if it has more, then we can still list more, but it's just time consuming. Okay? So let's take a quick example, a look at an example where listing is used. So we have a set A containing 4 members: Linda, John, Henry, and number 1. So we put these 4 members between two curly brackets. And we write A equal to open curly bracket, then Linda, John, Henry, 1 close curly bracket. So it is clear that A has 4 members or elements. And since Linda is a member of set A, we can write Linda belongs to A. And since Tong is not listed in set A, that means Tong is not a member of set A. So we can write Tong does not belong to A. And an important remark I want to point out here is that a member of a set is only counted once, even if it is relisted, which is shown in example 2. Okay, the set John Henry is considered the same as the set John Henry John. Okay, John is relisted, but it's only counted once. The second way of describing a set is listing with ellipses. It's similar to the listing method we just covered, but this time we do not cover all members. Usually it is because there are so many members to list. However, this time we have a pattern amongst members so that the reader can make an easy guess on what should be the next member, even if it is not listed. So let's take a look at such case. So we have this time a set A, which contains 2, 4, 6, 8, and then we use the ellipses. Okay, the reason is that, with the first 4 members or elements, 2, 4, 6, 8, it is quite clear that A is a set containing all positive even integers, which means that the members after the 8 is 10, and after the 10 will be 12, and then 14 and 16 and so on. So we don't need to list all of them. The next way to describe a set is called set builder notation. So this time we have a way to describe what elements belong to a set. Okay, and using what we call the set builder notation. So in this way, we will write the set H equal to, again, between 2 curly brackets. Now we only write the X, which is a representative, a generic representative, and then a vertical line or a semicolon. After that, it will be a PX. What is a PX? PX is what we call the set builder notation. It is usually a phrase, a sentence that describes the common properties of all elements of H. So let's take a look at an example for such case. So this time we want to describe a set A of odd even integers, which are between -99 and 49. So how do we do that? Obviously, we can list them all, but it will be very time consuming. You can easily see that. So this time, if we use a set builder notations method, then we only need to write A equal to, open curly bracket, X, the generic representative elements, and then the vertical line. And after that, it will be a phrase, a sentence which describe elements in set A. So we want A contain all even integers. So then obviously this X, whatever X is, has to be an integer, an even integer. And it has to be between -99 and 49. So this is the best way to describe the above set. It's very compact and clearly give the reader enough information to know which members or what is in A. So the phrase X is an even integer and between -99 and 49 is the PX in this case. Okay, next let's talk about the Venn diagrams. So Venn diagrams is a useful way to represent sets graphically. So when we use a Venn diagram, Remember I mentioned about the universal set which contain all possible objects in consideration. So U will be represented by usually a rectangle, a large rectangle. And inside this rectangle, we use other geometrical figures such as ellipses, a square, rectangle, circle, triangle to represent sets. So in this figure, we have three sets, A, B, and C, and they are represented by three different figures. And the elements of each of the sets are staying within each of these sets, each of these figures. Okay, the next concept and terminology used in set theories is the subset. So when we have two sets, set A and set B, we say that set A is a subset of set B if and only if every member of set A is also a member of set B. In terms of notation, we will use this symbol here. It is read as subset. It is the symbol for subset. So we read from again left to right. A is a subset of B. So with this, notice that B it can still be considered as a subset of itself because by the definition it still satisfies the definition. Okay, every member of B is clearly a member of B. So B is considered a subset of B. So B is this notation here. B is a subset of B is actually still a valid statement. When we want to emphasize that a set A is a subset of set B but not equal to B, then we can make it a little bit clearer. Okay, in this case we say A is the proper subset of B, and we denote that by dropping this bar underneath this inclusion symbol here, or we can put again the forward slash on the subset symbol, and in some textbook they also use the different symbol here to indicate that A is a proper subset of B. So sometimes when the proper subset is really not a matter or not important, we can drop the word proper. We just say subset only when we really need to distinguish whether econ is allowed or not. Then we can say proper subset. So let's take a look at an example for subset. So if we have set A containing three elements, 1, 2, 7, and B with 1, 2, 3, 6, 7, and 10, then it is clear that A is a subset of B, and actually more precisely it is a proper subset of B, because clearly every element of A is an element of B. However, A is not equal to B, so it is a proper subset of B. And when we use the Venn diagram, we will draw A inside B, the figures of A inside the figure of B. The next concept is called the empty set. And we denote the empty set by the symbol looks like number 0 with the forward slash on top of it. This is a special set that has no member at all. So that's why it's called the empty set. And because it doesn't have any member at all, that means it's always a subset of any set including itself. Okay, so that means if we are given any set, then empty set is always a subset of, if we're given any set A, then the empty set is always a subset of set A. And here we see that empty set is a subset of itself. Okay, so this is also a correct statement. Okay, the next one, okay, pay attention here. It is a little bit tricky. You have to really pay attention on the notation. So here, what do we see? In example 7, we see 2 curly brackets and then the empty set symbols inside. That means this is a set having exactly one element. That element is the empty set. Okay, so again, remember, these symbols denote a set containing exactly one element, and that one element is the empty set. So since empty set is an element of this set, we can write empty set belong to this set. Okay, the next example. Same set as in example 7. Okay, it's still a set containing exactly one element, which is the empty set. And remember, I said earlier, empty set is a subset of any set. So we can write empty set is a subset of this set. So that is also a true statement. Okay, the next concept we talk about is econ sets. So when we have two sets, we want to define when they are equal. It's very straightforward. The two sets are equal if and only if they have the exact same members. Okay, so here in example 9, it shows that the first set has 3 elements, 1, 2, and 3. The second set also has 1, 2, and 3. Although they are written in different order, it doesn't matter in sets notation. Now, in the third writing here, you can see 3, 3, 2, 1. Remember that we mentioned that in set notation, even if a member is relisted, it's still considered one single member. So the set 3, 3, 2, 1 is considered the same as the set 3, 2, 1, as well as the set 1, 2, and 3. Okay, so again, two sets are equals if they have the same members. Okay, now we talk about cardinality of a set. It's actually very simple. It's simply the cardinality of a set is the number of members in the set. It is denoted by the absolute values of that set. So if H has n distinct members, then the absolute values of S is n, which means with this red absolute value of S means the cardinalities of S or the numbers of members of S, which is n. If S is not finite, that means it has infinitely many members, then its cardinality is obviously infinity. It has infinitely many members. So example 10 give a quick look of cardinality here. So we have set A with 3 members, A, B, and C, 3 distinct members. Then we have absolute value of A is 3, which means the cardinalities of A is 3. The cardinality of an empty set is obviously 0 because empty set doesn't have any members. However, the cardinality of this set right here, okay, remember this is a set containing one member, which is the subset, which is the empty set. So since it has one member, its cardinality is 1. Okay? So try to really understand different notations here. Do not get confused. Okay, now let's talk about operations we can perform among sets. The first operation is called union. Okay, the union of two sets A and B we denote by this notation right here. A union B. This symbol is red union. It is like a glass standing upright. Okay. So this is the union of a set is defined to be the set containing all of the members in both set A and B. So it can be, the member can be from set A, can be from set B, or sometimes A and B share the same members, then it contains also those members. So basically everything from A and B is in the union of set A and B. Okay, so here's the set builder notation for the union. Okay, A union B contain all of the members in A or in B. In terms of the Venn diagram, you can see here we have set A, we have set B. When we talk about the union of A and B, that is the purple one right here. It contains all the members from A and B. Okay, so let's take a look at this example. We have set A containing 4 members, 1, 2, A, B. While set B contains B, C, 4, and 5. Then the union will be 1, 2, A, B, C, 4, and 5. The B is the common between A and B, and it's only listed once. We can also generalize this union concept to more than 2 sets. It can be a list of numbers of sets. And in this case, we use this symbol here. It still stands for this upright U. Still stands for union, and the index I indicate how many sets are involved in the union. But the definition stays the same. The union of any numbers of sets contain all members from each individual sets. Okay, the next operation among sets is the intersection. So the name already, or terminology already suggests that this is a set containing the common elements in both A and B. And in terms of notation, we use like the U upside down or the glass upside down. So in terms of set builder notation, the union or the intersection of two sets contain all members in both A and B. Now if we look at the Venn diagram, you can see that A is represented by the blue rectangle, and B is represented by the dark green rectangle. Their union is the one in common here. Okay, the tiny one. Okay, that is the set containing all members from both A and B. The shared one, the common one. Okay, so another example. If set A contains 1, 2, A and B, while set B contains B, C, 4, and 5, the only common elements between A and B is B, little b here. So the intersection of A and B is a set containing only one single member, that is the letter B. And also, similarly to the union, we can also generalize the concept, the intersection concept, to a collection of sets. So the intersection of a collection of set will be a set containing all the shares member among these individual sets. Okay, now we talk about intersection. There will be cases where the two sets do not have any common elements. That is when we say they are disjoint. Okay, so in terms of the set notation, their intersection has to be an empty set because there's no common element. Okay, so we write A intersect B equal to empty set. So below is one of short examples. A has 4 elements, 1, 2, A, and B. While B has 3 elements, C, 4, and 5. And clearly A and B have no common element at all. So in this case, we say A and B are disjoint. Or we can also write A intersect B equal to the empty set. Okay, the next thing we talk is the complement of a set. Complement of a set, this time we need to specify clearly the universal set. Okay? A complement of a set A with respect to the universal set U, it is denoted by the A prime. Is the set containing all elements which are not in set A. And that is described in this set builder notation for A prime. A prime contains all the X, which is in the universal set, and X does not belong to A. That means X is not in A. And this is a case where the universal set must be specified for the complement to be clearly determined. So, in this example, we have here A has 2 elements, 1, 3. U, the universal set, has 6 elements, 1, 2, 3, 4, and 5, 4, 5, and 6. Then the A prime is clearly 2, 4, 5, and 6. And you can see that if we use different universal sets, A prime will be different. So the complement is always relatively with respect to the universal set. Okay, there are 2 important remarks I want to make here. So the first one is obvious. A set A and its complement A prime are always disjoint. They obviously don't have any common element. Why the unions is always the universal set. The second remark is just about the notation. In some textbook, instead of using A prime, the A bar, A upon bar is also used. Okay, here's a look of the Venn diagram of set A and its complement A and A prime. A is represented by the blue rectangle, while its complement A prime is the yellow area. Okay, here's a list of some popular set identities. And some of them actually are quite obvious to see why they should be true. The rest need to have some proof. Right now, it's you just take a look and see some to be familiar with some of this law. So for example, the identity one is quite obvious. If we take A union B is obviously the same as B union A. Intersection, we can also switch positions between A and B. The associative law is also easy to see. If we have just union operators, then we can do the association. Okay? A union to B union C is the same as take A union with B first and then union with C. The same also holds true for intersection. Now the distributive laws require a little bit more work to see why they are true, but it's still not too difficult to see if you draw a Venn diagram. The complementation law is also easy to see. When you take complement of complement, you get back the original set A. Because complement of A prime is by definition the set of all elements which is not in A prime. If they are not in A prime, they have to be in A. And the De Morgan's law is quite famous here. So when you do the complement of the union, you basically distribute the complement operation, but you have to switch the union to intersection and vice versa. So complement of A union B is the same as complement of A intersect complement of B. And complement of A intersect B is the same as complement of A union complement of B.